What's going on, guys? Welcome back to this video. Today we're doing HackTheBox, and in this video we're going to carry over with intro to binary exploitation track, reminding you that this is the second challenge in this track. The first challenge we did Jeeves, and today we're doing Bat Computer. All of these challenges, if you understand them and follow with me thoroughly, you will be able to at least to figure out or to uncover buffer overflow vulnerabilities in any binary, and hopefully with a bit of coding knowledge you'll be able to create the relevant exploit and exploit buffer overflows. Let's go back now to Bat Computer. This is the example of today. So after we start the instance and download the required files, let's now jump to the virtual machine. So in here, what do we have? So we have the zip file, which when we unzip, it will return the Bat Computer binary. Okay, as with any buffer overflow, or let me call it binary exploitation example, we want to understand the nature of the file. So file Bat Computer, as you can see, it is a 64-bit executable file, and notably, guys, it is stripped binary. So a stripped binary is a kind of protection that prevents you from doing two things. The first one is setting a breakpoint at the main function. In order to set a breakpoint at the main function, when dealing with stripped binaries, you will have to extract first the address of the main function. So it's not like you do b main plus something. That's how we do a breakpoint in GDB debugger, right? But in that case, or in the case of today, it is a stripped binary, which means we have to find first the address of the main function, and then we use the address to set the breakpoint. Additionally, stripped binaries are normally harder to reverse engineer. That's the first two things to note about the Bat Computer. Now, the next thing we want to do is to check the protections on this binary. For that, we're going to launch GDB -q bat computer, and then we say check sec. Take a look here. So we have all of the protections are disabled except we have the pi enabled, and here this one, when it is partial, it means some parts of the code can be modified, some parts. Now this one is enabled, the pi. I've explained all these protections in my BOF note file, which you can find it by subscribing to the channel membership. So Position Independent Executable, right? It means that the dependencies of the binary are loaded into the memory with random addresses every time the application is executed. Again, it makes it harder to reverse engineer and find specific addresses for specific functions like the shell and bin, or the system function. Now this one is partially enabled. It means that some sections can be modified. Now the thing is, NX is disabled, which means we can execute code in the stack. When NX is enabled, we cannot execute code in the stack now. So that's the thing that got our hopes so high about this binary, because NX is disabled. We can execute code now in the stack. Alright, the next thing now, let's open a new tab. And in the new tab, let me check if Ghidra is running. Oh, so Ghidra is running. Alright. So when we open Ghidra, as you can see, we are going to functions to find the main function. We see these functions. It's not clear which one of them is the main function. So to be able to do that, to find the main function, we're gonna go to Window, and here we check define strings. In the define strings, we can check all of the strings in the function or in the code. If you scroll all the way down, we can see the start of the function. Welcome to your Bat Computer. And let's go to the assembly view here. After this statement, as you can see, we have this function, and we have it was very hard. So in between, we have this function here. This one could be the main function. So how do we jump to this function? We're going to go to functions and find the exact same one. So it is here. We're gonna close the strings, and this is the main function. Let's take a look at the code here. So I have a couple variable declarations. Among them is AU stack with 76 bytes and AC stack with 16 bytes. And then we have a call to a function, and then we have a while loop that looks like repeating itself while a specific condition is true. So here it's set, it allocates for this variable, and then we have this statement, and then we have an if statement. So if this variable local 16.8, which happens to be here, defined, where it is defined, yeah, it is here. It's defined here. It's taken as user input, by the way. So if the user inputs, or if you actually send 1, if you didn't send 1, okay, and you did not send 2, it's not gonna enter into this if statement, and it's not gonna enter into this if statement. Okay, now suppose that you didn't enter 1 and you entered 2, it's gonna ask you for a password, and it's gonna check if the password is equal to this string. If it is equal to the string, it's gonna ask you to enter a command. Now, of course, this is not a system command. It is just any string you can provide or type. It's gonna read 137 bytes into the AU stack 54, which was defined here, 76 bytes. So here's the vulnerability. The vulnerability lies in line 31, where it asks the user to provide an input of the size maximum of 137 bytes, as you can see here, to store it in a variable which was defined as 76 bytes. So here's a buffer overflow vulnerability, this line. All right, so what's the objective now? The objective is to, the first thing, we want to enter this if statement. So what we're gonna do, we're gonna provide the application with what it wants to enter this if statement, which means we're gonna set the input to 2, and then we're gonna enter the password as equal to this password, and then we're gonna be asked to enter some commands. Now we know these commands that we're going to enter, in order to cause segmentation fault, we have to achieve 2 conditions. The first one is to enter something bigger than, as you can see here, 76, which is the size of the buffer. You can also just enter 137 bytes or maybe 138, but this alone will not cause segmentation fault. Guess why? Because after I enter the input, it's gonna print this out to the screen, and then it's gonna go back to the while loop here. So while the while loop here, we are kind of stuck in the while loop here until we provide, or until we input something that is neither 1 nor 2. If we do that, we're gonna then jump to the return function, which is what we want. So segmentation fault, the first thing we're gonna do, we're gonna generate a pattern that is more than 76 bytes. Okay, and then we want to jump to return 0. After we provide the input, which is more than 76 bytes, we're gonna again repeat the while loop here. It's gonna ask us for 1 or 2. We're not gonna do that. We're gonna enter something that's neither 1 nor 2, and it's gonna now jump to the return, demonstrating that we have a segmentation fault because, as I told you guys, we have entered something that's more than 76 bytes. Let's do that. Okay, so here we're gonna generate a pattern. So pattern create. Remember, we need the pattern to be exactly 137 or less. So here the application is expecting 137 bytes or less, because if you create more than a pattern that's more than 137 in bytes, what's going to happen? The application will take the 137 bytes, and the rest will be used as an input to the while loop while reiterating the while loop. So we're going to create 137. You can create less, but if you want to hit the segmentation fault, make sure that it is more than 76 bytes. So create, and then we have the pattern. So we're gonna say R2 because we want to enter the second if statement, and then we're gonna provide the password. No, what's that? Okay, this is the password. Okay, we go back now. Alright, now the commands. We're going to provide the pattern that's equal to 137 in bytes, and that's more than the allocated buffer size, which is 76 bytes, which will cause the segmentation fault. Segmentation fault? Oh, no. So, is it no or is it yes? I guess you know the answer. Of course it is yes, but we don't see it yet. And the reason is, as you can see, this was printed out to the screen, and that's right, and then we are back to the while loop. So the execution flow will come here, prints this out, and then it comes back again to the while loop, and we're not gonna hit the return address. Now there is a segmentation fault in the program, but we want to see it. In order to see it, we're gonna have to reach the return address. So we're gonna need to provide an input that's neither 1 nor 2 to break out of the while true. This is the correct timing of breaking out the while true after we have achieved a segmentation fault. So 3, and now we got a segmentation fault. So after getting the segmentation fault, we want now to find out what's happening in the registers and the stack as well. Okay, I'm gonna go up, and here we see that the instruction pointer now points to the return address, which is what we want. So remember, in buffer overflow, we want to calculate how many bytes there is that we need to reach the return address, because these bytes will generate them with anything you want, and then after reaching the return address, we want to replace the return address, or the memory of the return address, we want to fill it with a shellcode. So we'll have to find out how many bytes there is to reach this address. There are many ways to accomplish this. One of the most popular method is through, as you can see, generating or finding the offset. We want to find this. Let's go back here to the scenario where we exploit buffer overflow over an unprotected binary. This is the scenario here. As you can see, we need to find the offset. So that's the command to find the offset. The value here is, we need to find out the value that is in the stack pointer. The stack pointer here, this is the value in the stack pointer now. Okay, now to find the offset, we're gonna have to use pattern offset and see what is in the stack pointer. We can copy this, all of it, but if it doesn't return an offset, you can copy the first 2 or 3 characters. Let's try with the first 2. So it is at offset 84, which means we need exactly 84 bytes to reach the return address. Okay, so what do? Like always, guys, it's the same drill. We need NOP or padding just to prevent any abnormalities in the execution flow, the shellcode, and the address of the instruction pointer. Now in the scenario here, we're not going to put the instruction pointer address. We're going to use the address that's leaked in the code. So remember, when we explain the code, the analysis here refers that if we enter 1 during the execution of the code or the binary, it's gonna print out, as you can see, the address of what? Look at this. It's the address of the input, or the variable that stores the input. And that's what we want, because in buffer overflows, in order to reach the return address, you have to calculate the distance between the address of the beginning of your input and the address of the return address. The result of this subtraction operation, it will give you the offset, or how many bytes. Now, normally we found it's not actually scalable to subtract hex hexadecimal addresses all the time. That's why we use pattern offset. 84. So 84 is the number of bytes, or the difference or the subtraction between the address of the beginning of the input and the address of the instruction pointer or the return address. So the operation, or sorry, the result of this subtraction is equal to 84, this is the offset. So now we know what to do. Let's now run again and put 1. So look at this one. This is the address of the input. Okay. Now there is another method to find this address. If you don't want, let's say it wasn't given in the code, we have to set a breakpoint at the main function. Remember that the binary is stripped. So to achieve a breakpoint, we're gonna have to execute Control-C and abort the execution. And then we say trace call Control-D. And as you can see, guys, this is the address of the main function. Now let's set a breakpoint here. That's what I was talking about. So you have to use the address of the main function. We paste, and now we set a breakpoint at the main function. Let's run now. As you can see, when we run the application, we didn't receive the prompt to enter our selection 1 or 2. We hit a breakpoint at the main function, right? So let's go back to the code. So now the execution flow is here. Now we are here. We cannot execute now the main function because the breakpoint is right here. So to find out the address of this variable, or the beginning of the input, okay, what we have to do, we have to find out the address of all the instructions until we reach this one. When we reach line 31 in the assembly language or in the assembly code, we're gonna be able to learn the address that is needed to set the second breakpoint. We want to set the second breakpoint here. Okay, when we set the second breakpoint here, we'll be able to find the address of this function or this variable, because this is the line where it stores the user input into the variable O stack, which will reveal the address of this variable. So x/70i, here we reveal the addresses of the next 70 instructions. And as you can see, we have this read. This is the call to the read function, as we showed in the code. And then right after this, it is loading the effective address to be able to store the value of the input. So now the next breakpoint, as you know, as you guessed, will be here. So we're gonna first take a look at the breakpoint. We're gonna delete the first breakpoint that was set at the main function, because now we want to resume the execution. And now we're gonna set a breakpoint at this address. Okay, now run. So here we say 2. Okay. Now the next thing, we want to provide again the user input. So the user input can be anything, like it can be 137 bytes to code the segmentation fault. So let's enter 170 bytes. These are 138 bytes. I'm gonna skip the last A. And now we hit the second breakpoint. Now let's take a look. Going up, this is the stack pointer now. And as you can see, the instruction pointer points to next instruction, which will take the input here that you provided and store it in the variable, into this variable, AU stack 54, which is the variable whose address is wanted. So now after we set the breakpoint exactly at this point, we can find the address of the input by using pattern search. So pattern search, and we can input the A's. This should return the address. Okay, let's try. Not found. Okay. Okay, let's look at the stack. So as you can see, this is the password, where the password is stored, and then we have this address, and right after this address we have the A's. So the address of the input is between, as you can see, this address and this, and there is 8 bytes between them, which means that the correct address or the start of the input is at the exact same one here. Instead of 0 we have 4. Okay, so what to do now? We now have the address of the input, or the beginning of the input. The next thing you want to do, guys, is to resume the execution and hit the segmentation fault. So R, so here we're gonna do info break delete 2 R, R, and then we say 3. We didn't have segmentation fault for some reason. Let's try one more time. 2 and the password. Let's see what's the password. Okay, now 137 bytes. 3 segmentation fault. Now we have the address of the memory address of the return address. Now we subtract this. Remember, subtract the return address from what? From the beginning of the input, which was here. Remember to replace 0 with B, 0 with 4. The result of the subtraction will equal to 84 in decimal, of course. But you're not gonna do that every time. I'm just breaking down how it works. Okay, you're just gonna use pattern and offset. Okay, pattern offset pointed to 84 bytes. Now it's time to craft the exploit. Let's go back. This is the exploit code. Now import the all the pawn tools, and let's make this a bit bigger. All right. So first, since this is a challenge that is done over the web, we're gonna have to specify the connection parameters, the IP address and the ports. We're taking exactly from here. This is how you connect the binary, and then we have to mimic the output of the binary. So if you go back to the binary itself, or we have to feed this into the code. Okay, all of them. I'm gonna go back. As you can see, this is the beginning of the code, and then we have the stack base. The stack base is the address of the beginning of the input. It was leaked in the code. Okay, so what you have to do, you can go back and say 1, and you have the stack base address. This is the beginning of the input. So we're gonna take it and put it in the code here. But what we have to do, guys, don't forget to specify 0x, because this is a string and the code will read this only. So you have to manually append the 0x. Okay, connection receive, and then we decode this using the Latin. We explained this in the previous challenge, by the way, to make sure that you convert correctly from byte to strings. And then you send 2 now. So basically first you send 1. After you send 1, you're going to receive the leaked address. So the code will enter 1, and the code will read this line and store this address in the stack base. The next thing, we're going to resume the execution of the program and enter 2. We enter 2, we're going to be asked to provide the password. So we send the password in a new line, and then we craft the payload. Like always, guys, when there is no binary execution protections on the payload or on the code, your payload consists of 3 parts. Remember from the notes. It consists of a padding, the shell code, and the address. Now that's the rule all the time, but sometimes you have to change the order of these according to the scenario. So normally we would first put the padding or the NOP slit first. Normally the NOP slit will equal to buffer size. The buffer size here is the offset, which is 84. So we have 84 minus the length of the payload. So the first part is the shellcode. We generate the shellcode using the shellcraft function. This will result in a shellcode, and then the shellcode will be added to the padding. Now the padding is the same formula here. So here, the pattern we generate, so we generated A's, okay, and we multiplied them with the result from the subtraction operation between the offset and the length of the payload. That's how you calculate the knob slit or the padding all the time. So this one, the padding plus the shellcode, and lastly plus the address. So here we put the address that was leaked first in the code. And I showed you guys, if the code or if the memory address wasn't leaked in the code, I showed you guys how to find it a while ago. Now we use P64 because this is a 64-bit binary, and we sum all of these to form the final payload. We send the final payload here in the next line, which corresponds to, as you can see, 2. So the code now entered the password, and then the next line will be sending the payload. And then remember that after we send the payload, we want to hit a segmentation fault to break out of the while loop. So we enter 3, and then we get interactive login or interactive shell. Let's test that in action. New line. Python 3 exploit code. I'm gonna have to see if that's code. So as you can see, we switch to interactive mode, and then we have the shell ID, root, ls, and now you have the flag. So that was it, guys. Remember to review all of my videos on buffer overflows to make yourself stand on good grounds regarding this sort of vulnerabilities or regarding binary exploitation. And if you want extra, you can just find the node file here by subscribing to the channel membership. So that was it, guys. I hope you enjoyed that, and I'm gonna see you in the next video.